Hi everyone, in this video we are going to discuss this problem called maximum number of points from grid queries. So the problem says that we will be given with a matrix of m cross n dimension and we will be given with k number of queries. For every query we have to find out the maximum number of points that we can get, and to get points we have to start from the top left corner and we can move to the adjacent cells if they have a value strictly smaller than the given value of the query. Okay, and the points will be equal to the number of nodes or cells that we can visit from the matrix. So let's take an example and try to understand the problem statement. So let's say we are given with this matrix and we are given with these three queries, right? So the first value in our queries is 5. So we want to find out what can be the maximum number of points that we can get for value 5, right? So for that what we'll have to do, we will have to start from the top left corner, which is this one having value 1, right? So this cell is having value strictly smaller than 5, right? So we can visit this. Now the adjacent of this one is 2 and 3, and both of these cells have value smaller than 5, so we can also visit these two elements. Now the adjacent of these two elements is 4, 5 and 4, right? And for this value 5 we can visit this cell, we can also visit this cell because they both have value smaller than 5, but we can't visit this cell because this is not having strictly smaller value than 5, it is having equal value, right? So we will not be able to visit this. So let me just remove this. Okay, so now the adjacent of this 4 and this 4 will be this 7 and this 5, and they both can't be reached, or we can't consider these cells because they both have value greater than or equals to 5. That means they don't have value strictly smaller than 5, so we can't visit these nodes. So we can say that we will be able to only visit these 5 cells or nodes, right, for this particular query. So the answer for this query will be 5 because we are able to visit 5 nodes from this matrix. So the score will be 5. Okay. Now let's talk about 6. So for 6 we will again start from 1, right? And we will be able to visit it because it is having smaller value than 6. Then the adjacent of this is 2 and 3, and both can be visited because they both have value smaller than 6. Now the adjacent of these two elements are 4, 5 and 4. So they all can be visited because they all have values smaller than 6, right? Now the adjacent of these three elements are 7 and 5, but we can't visit 7 because 7 is having value greater than 6. We can only visit this 5, so we can visit this 5. Now the adjacent of this new node is 8, and 8 can't be visited because it is having value greater than 6, right? So for this particular query we will be able to traverse these nodes. And how many nodes we have? We have 7 nodes. 3 plus 2 plus 2, right? 3 plus 2 5 plus 2 7. So for this query the answer will be 7, or we can say the maximum number of score that we can have is 7, right? Now let's talk about 3. So for 3 we will again start from the top left corner and we can say that we will be able to visit 1. Then after that the adjacent nodes of this is 2 and 3. So we will only be able to visit this 2. We will not be able to visit 3 because they both have values, equal values, right? So we will not be able to visit it. So in case of 3 we will only have 2 nodes which can be traversed. So the score will be 2, right? So these 3 will be the answer for these 3 queries, right? So we have to return a vector containing all of our answers in the same sequence as queries, right? So this is what the problem says. So now maybe we can try to think of a way in which we can try to solve this or approach this problem. Okay. So to solve this problem, can we say that we can run a BFS or DFS for every query starting from this particular node, or we can say top left corner, and then we can visit all the nodes that are having value strictly smaller than the given query, right? So for 5 we will be able to visit all these nodes, and then for 6 we will be able to visit these nodes, and then we can simply count that how many nodes we were able to visit, and then we can return that answer, right? So as a brute force we can think of this solution. So okay, now if we run a BFS or DFS starting from this top left corners, then what can be the maximum time complexity or maximum number of operations that we will do if we run a BFS or DFS starting from this top left corner? So we can say that at most we can visit all the cells of the matrix, right? That will take m cross n time, right, for a DFS or BFS. Now we are saying that we will do this thing for every query, right? And we are given with k number of queries. So can we say that in worst case we might have to do these many operations or work k number of times, right? So we can say the worst case time complexity will be order of k into m into n, right? If you go by the brute force solution of running a BFS or DFS for every query, right? So now let's try to think of a optimized way. how we can reduce the number of operations that we are doing in the brute force approach. So can you observe one thing? Can we observe one thing? Can we say that for 5 we will visit these 5 nodes, or we can say 5 cells, and they all have values strictly smaller than 5, right? Now for 6, when we will run a BFS or DFS, then can we say that we will revisit all these nodes? Can we say this thing? Because if these nodes have values smaller than 5, then for sure they will have values smaller than 6, right? So for 6 we will again revisit these 5 elements, and besides them we might visit few new nodes or new cells, right? So now based on this observation, can we say that if we are given queries in ascending order, in that case can we say that we will be doing redundant work, we will be doing the same work again and again? For example, let's say if we just move this query 3 in the starting, right, then we will traverse these 2 nodes first for 3, right? Now for 5 again we will traverse these 2 nodes, right? And for 5 we will traverse 3 new nodes also. But for 6 we will again revisit all these 5 nodes, right, here, and we will visit few new nodes also, right? So we can say that if queries are given in the ascending order, then we will be doing redundant work, we will be doing the same work again and again. So can we think of something such that we don't have to do this redundant work? Can we think of something? So first thing what we can do is we can try to sort the queries which are given to us, right? And we will also store the initial indices they will have. For example, this had the initial index of 2, then this had the initial index of 0, and this had the initial index of 1. So that after sorting, if the sequence changes, then we also know that original index, because we also have to return this vector in sequence, or we can say the original sequence which was given to us in the queries, right? Okay. Now what we can do is for 3, when we will run a BFS or DFS, then we will visit these 2 nodes and we will say that the maximum number of score for 3 is 2, because we were able to visit 2 nodes. Now for 5, we know for sure that we will be able to traverse these 2 nodes, but we don't want to visit these because that will just do the redundant work, and we want to reduce the number of operations that we are doing. So for that what we can do is we can skip these 2 nodes and we can try to pick the adjacent of these 2 nodes. And what are the adjacents of 1 and 2? Adjacent of 1 and 2 is this 4, which is here, and this 3, and we have this 5, which is adjacent to these 2 nodes, right? Now what we can try to do is we can try to run the BFS or DFS, that whatever we are running, from these 3 nodes. Instead of starting from the top left corner, we can start our DFS or BFS from these 3 nodes, and we can try to visit the nodes which are having value strictly smaller than 5. So if we run a DFS from 3, then we can say that 5 is adjacent, but it is having greater value, so we will not consider this, but we can move to this 4, which is also adjacent, and 4 is having value smaller than 5. So we will be able to visit this for sure, right? So we can consider this in our current traversal, right? And now we can try to go to the adjacent cells of 4. So 4 is having 5 as adjacent node, but this is having greater value, so we will not visit it, okay? Cool. So similarly, this 5 is also having greater value, equal value, so we will not consider this. Now for this particular 4, we will try to traverse the adjacent cells of this 4. So we can say that this 7 is greater than 5, so we will not consider this, and 2 is already visited, so we will not try to visit 2. Okay. So in that way, can we say that we saved 2 operations for us, right? Which we would have done in our brute force approach if we would have started from top left corner, right? So not visiting already visited nodes is saving us some number of operations. Similarly, for third query, for value 6, instead of running our DFS or BFS from top left corner, what we can do is we can try to run the BFS or DFS for the adjacent nodes of these elements. Instead of running from 1, we can start running from this 5, because this is adjacent to this 2 and 3, right, which we have already considered. And we can run a DFS from this 5 also, because we have already considered 4, right? So this will save us 5 operations here, because we will not visit these 5 nodes again, right? So cool. Okay, now let's try to use this idea. So again, let's say for query 3, we will start from top left corner. So we will start from 1, and 1 is having value smaller than 3, so we will consider it. Okay. Now once we have considered this cell, we will try to go to the adjacent cells, which are 2 and 3. So we will try to go to the adjacent cells, which are 2 and 3. Now 2 is having value smaller than 3, so we will consider this element. Okay. And if we have considered this element, then we will try to go to the adjacent cells of 2. So 1 is already considered, so we will say that we will try to consider 4, and we will also try to consider 5. Okay. Now this cell is having value 3, which is equal to our query. So we will not be able to consider this element in this particular query. Okay. But we know that we have already traversed these two elements, and we also have traversed these elements, but they have a value greater than or equals to 3, which might be smaller for the next queries. So we will try to have them with us only. Okay. Okay, now for second query where the value is 5, we will not be interested in these two nodes. Why? Because these two nodes have values smaller than 3. So for sure they will have a value smaller than 5. So we already know that these two nodes will be considered in our this query where value is 5. So we will not be interested in these two nodes, but we will be interested in these 3 nodes. Why? Because they might be smaller than 5 or might be greater than or equals to 5. So we will try to traverse these 3 nodes further. Okay. So we have 3 in the queue next, or we can say next node is 3. So we will try to traverse 3, and 3 is having value smaller than 5. So we will be able to consider this in our current query. Now for this 3, we will, let me just write it here, 3, 4, 5. Okay. Now for this particular 3, we have already considered this here, right? We have already considered here. Now for this 3, we will try to go to the adjacent cells. So we can say that this 5 is already present in our queue, we can say, right? So we will not consider this. Now if we talk about this adjacent cell, then we will try to consider or put it in our cell, right? So we can say we will put it in the queue. Okay. Now let me ask you one thing, like this 4 should come after this 5 or before this 5? So this 4 should come before 5. Why? Because 4 is smaller than 5. And because 4 is smaller than 5, this 4 is having higher probability or chances of being smaller than a query which we are currently considering or we will consider in the future, right? So 4 should come first because it have more probability of being smaller. So we will put it in front. Okay. Okay. Now for this particular 3, we have considered the adjacent cells. Now the next element which we are going to consider is this 4, and 4 is smaller than 5. So we will be able to consider this 4, right? Now we can, now it does not matter like which 4 we pick, we can either pick this 4 or this 4. So let's pick this 4 because it was inserted first. Now for this 4, we have traversed, right? Now we will try to go to the adjacent cells of 4. Now for 4, 2 is already considered, like already visited. So we will not consider this, and 7 we will try to consider. So we will put 7 here. Okay, cool. This 4 is smaller than 5. So this will also be traversed, right? And we will also, we'll remove this from this remaining queue. Now we'll try to go to the adjacent cells of this 4. So adjacent cell of this 4 is this 5, this particular 5, and 3 is already visited, so we will not consider that. So we'll put this 5, and we will put this 5 not after 7 but before 7, right? Again, why? Because 7 is having less probability of being smaller than a query which we are currently considering or will consider in the future, and 5 is having higher probability, right? So we will put it first. Okay, cool. Now for this particular 5, there is no element which is strictly smaller than 5, so we can't consider any element, right? So these are the 3 remaining elements, and these are the 3 new elements that we have considered. So in this case, the answer will be 3 plus 2, and this 2 is because we have already visited these 2 nodes for 3, and 3 more nodes we have considered for 5. So in total, we will be able to visit 5 cells for this particular query. Okay, now let's talk about the third query. In third query, we know that we are not interested in these 3 elements or these 2 elements. We are only interested in the remaining elements that, or we can say these are the first elements that will be considered after this. See, right now we have covered all these nodes, right? So far we have covered all these nodes. So if we have covered all these nodes, then the first nodes after these nodes that can be traversed are 7, 5 and 5. And all these 3 are present in our this queue, or we can say, we can call it as a remaining queue. It contains the elements which are remaining or which needs to be considered next. Okay, cool. So here what we are saying is that instead of considering these 5 nodes, we will consider these 3 nodes to start our traversal, right? So first node that we will consider is 5. Let me just write it here, 5, 5, 7. Okay. Now 6 is having value greater than 5, so we will traverse this and we will remove this from this queue. So let's say we removed this queue, like we visited this queue, so we will try to go to the adjacent cell of this 5. So this 7 is already present in our queue, we have already considered it, and this 5 also we have already considered, right? So no adjacent will be, is not remaining, we have already considered all the adjacents. Now this 5 is also having value smaller than 6, so we will move it here, or we can say we will visit it, right? Now all the adjacent of this we will try to put, or we will try to consider. So from this 5 we have this 8 which is not visited yet, right? So this 8 we'll try to put it in the queue. So it should come after 7. Okay. Now we'll try to consider the 7, and 7 is having value greater than 8. So we can't consider these two elements, right? So in that way we can say that we will be able to traverse 2 new nodes, right? So we were able to traverse 5 nodes till here, like, right? And for 6 we were able to traverse 2 more nodes, right? So can we say that the answer for this particular query will be 2 plus the answer that was for 5, which is 5. So 5 plus 2, 7. 7 will be the answer for this. Okay. And once we have this information, then we can generate our resultant vector, and then we can return that. So in this approach, can we say that every node will be traversed or visited only once, at most once it will be visited, right? So the time complexity of that particular BFS or DFS traversal will be m into n. But there is one more interesting thing, and that is this particular queue. Like we can say that we have 2 queues, right? In one in which we are marking all the visited nodes, we are like storing all the visited nodes, and one queue in which we are storing all the next nodes that are going to be considered, right? So, and we are also saying that we want a sorted order in this queue. So can you guys think of a data structure which can store some number of elements in a sorted fashion, and we will be always interested in the first node of that, right? Like first we will consider this, then we will consider the next element, and so on, right? But the major requirement is that we want a data structure which can help us in storing some number of values in sorted order, and that can give us and what operations we want. We want insertion, and we want deletion also, because we want to remove nodes and put it into in this particular queue. So we want a deletion also, right? So insertion, deletion, and we also want to traverse or access the first element, right? So what data structure can give us a sorted order and can also give us these two functionalities in an optimal way? So can we say that we can use a set, ordered set, right? We can use set or map. Like set will be better because we just want to store one value. Actually we'll have to store 3 values, but for now we can just assume that we will have to store one value. Okay, cool. And in set there is a problem that, like, not a problem but a property that that every key should be unique, right? So either you can try to use multi-set, or what you can do is you can store value comma x and y coordinate, right? We can store these 3 values as a key in the set so that it will be unique. Okay. Okay, now maybe you can pause the video and try to implement this logic. Okay, now let's try to write a pseudocode for this problem. So the first thing that we will need is set, right? We will require 2 sets. Now we've already seen that we will store 3 different values. First one will be the value of a particular cell, then the x coordinate of that, and then the y coordinate of that, so that we do not have same values, because set requires unique keys, right? So just to make keys unique, we will store value x coordinate and y coordinate, right? That will be a unique pair, right? So for that, what we can do is we can either use a vector of size 3, or we can use a pair of pairs, right? So we are going to use pairs. So let's say we have a pair which will first store the key, or we can say the integer value of a cell, then it will store the x and y coordinate of that. So integer, all right? So this portion will store x and y coordinate, and this portion will store the value, right? So we will require okay, let me just write one more thing. So for this, because we are passing 3 values, so we will also have to write our own comparator, which will basically sort things for us, first based on this value and then later based on x or y coordinates, right? So CMP. So I assume that you guys will be able to write this custom comparator, and we will require 2 different sets. First is this MP, and let's say the second one is temporary. Okay, cool. Now we will also require a vector of vector to which can store which cells we have already visited, right? We can say that we want a grid which will represent which cells have been visited, and you can, like, we can give the dimension of this as n cross m, right? Now we need to traverse starting from 0th query till the last query, and I'm assuming that we have already sorted the queries and we have already stored their original indices, right? So now if we have sorted the queries, then we can start from the first query and then we can try to find out that how many cells we can visit, and then we can keep on moving forward, right? So let's say we start from I is equals to 0 and we will move till k, and every time we will try to consider let's say q is the vector which is storing a pair. Q is basically a pair. We can assume vector of a pair, and it will store the ith query and the ith and the original index of that ith query, because we are going to sort that thing, right? So this will be the q query, or we can say a vector in which we will be having our queries. So in this, q of I will be representing the ith query, where q dot I dot first will be referring to the value of the ith query, and then dot second will be referring to the index of that ith query. Okay, cool. Now for this particular value, we have to find out that how many new nodes we can traverse. And we are assuming that in this map MP, we will be storing the nodes that we are going to traverse next. Okay, so we will consider all the values that are present in this map. So for that, we will start our traversal. Let's say this, we can use this auto keyword, then J, and then we can iterate in map. Okay, we can pass it in, pass this thing by reference. Okay, now here J will be referring to one of the we can say elements of this map, and in this J will be a pair of pairs, right? So J dot first will be referring to the value, and J dot second dot first will be referring to the x coordinate of that particular value, and J dot second will be referring to the y coordinate of that particular cell. Okay. Now first thing what we need to do is like we will be running, let's say, a DFS. We will be running a DFS to traverse the new nodes. Now we will want to run DFS if and only if the value which is present in the jth element of this map is strictly smaller than this particular value. If it is greater than or equal to, then it does not make sense to run any DFS, because we will not be able to traverse that particular element, right? So first check we can have is that we will run a DFS if and only if q, this value, this is the ith query, right? If it is greater than, strictly greater than J dot first, and J dot first is nothing but the value of the jth element in this particular map. Now if this condition is true, then we will run a DFS. So let's say we will run our DFS. Okay, in this we will pass everything that is required, and also we will pass this temp. We will pass this temp set, and whatever elements after traversal which will be having greater value than this particular value, they will be stored in this temp. That means the values that can't be traversed for this current query but will be considered in the next query will be stored in this temp, right? So we are assuming that this DFS will visit, like mark everything as visited, whatever we will visit, and then put the values which are having greater value than this in this particular map. Okay. Now let's say it will return the number of nodes that it traversed. So let's have a variable current, right? And we can say for this current will be initialized to 0, and then we can increment this count. So this current will store the number of nodes that is traversed in this traversal, and it will be incremented. Okay, cool. So after this condition, what we can do, we have traversed the jth element. So what we can do is we can now remove this jth element from this map. So for that, what we can use erase. So mp dot erase, and for that we will first have to find out the pointer to this, and that we can do is using this mp dot find j. Alright. So this will first find the jth element, and it will return the pointer to the jth element. Then that pointer will be removed from this map. Okay, cool. Now if this condition is not true, that means this element and elements after this j will be having value greater than or equals to this particular value. In that case, we will not be able to traverse anything, right? So in that case, we can get out of this traversal or this loop. So in that case, we will break. Okay. Now after this for loop, we will be sure that this current is holding the new nodes that we were able to traverse for this particular query, and this temp will be holding all the nodes that were having greater values than this query, and that might be smaller than the new queries, right? So what we have to do is we have to shift all the elements present in this temp to this map MP, set MP, and we also have to find out answer for this current query. So the answer for current query will be equals to the total number of nodes that we were able to traverse so far plus the number of nodes that we have traversed in this particular traversal. So let's have a previous variable that will start from 0, and our answer will be answer for this query qi dot second. Why we are doing this? Because this is ith query, and the original index of this query is q of I dot second. This is the original index of this particular query, and at this index we want to store the answer. And what is our answer? Our answer is current plus previous. Previous will store all the total number of nodes that we have traversed so far, like before this, before considering this ith query. Okay. Now we will update this previous. So previous will become plus equals to current. Right. It was holding the total number of nodes that we have traversed so far. Now we are adding the new nodes that we have traversed. Right. So for next query, this will become the previous. Okay. Now after this, we need to move everything from this temp to this map. Right. So move all the elements of temp to MP. For that you can write a for loop and you can move everything, right? And after that what we can do is we can clear all the content of this temp. So temp dot clear. Okay, all right. Okay, now after this we will be sure that for every query we will be having our answer in this particular vector, and we can return that. All right. So this will be a pseudocode. I am assuming that you guys will be able to write this DFS function, and you guys will be able to also write a logic for this thing, and you guys will also be able to sort the queries and store their indices and everything, right? Which we have abstracted for now. All right. Okay, now let's talk about time and space complexity for this particular problem. So, okay, so this query, like this loop will run k number of times, right? This loop will run k number of times. Now for all the k traversals of this loop, can we say that this DFS will run for at max m into n number of times? Because in DFS what we are doing, we are traversing a cell and we will be traversing each cell at most once, right? We will visit each node at most once, right? So we can say that it will traverse for all the iterations. This DFS will run m into n number of times, right? Now this the time complexity of this is independent of k. Why? Because we know the total number of operations that will be done by this DFS, and that will be m into n, right? Okay, now every element will be pushed inside this map and removed from this map at most once, right? And what is the complexity of insertion and deletion in map? It is log of size of that map, right? And just to take an upper bound, we can say that the size of this map will never exceed m into n. So can we say that for every insertion or deletion, the time complexity will be m into n, right? And this thing will be done for every node or cell at most once. So how many cells or nodes we have? We have m into n cells, right? So the overall time complexity of this particular thing and this particular thing will be m into n, log of m into n, right? And the time complexity, independent time complexity of this DFS will be m into n, right? And then this loop will run k number of times. So can we say that the total number of operations will be k plus m into n plus this thing, right? And we always consider the maximum value, so the overall time complexity will be this thing. Okay. Now why we got addition here? Why didn't we multiply this? The reason is simple, because irrespective of the value of k, we know the total number of operations that will be done by this DFS, and we also know the total number of operations that will be done by this map, and like this deletion and these insertions, right? So now that's why we are adding these values. Okay. So that was one of the ways to go about this problem. And instead of using a DFS, we could have used a BFS, because at the end of the day, we just want to traverse new nodes which are having values smaller than the given query, right? Strictly smaller than the given query. Now let's say we do not want to go by this method. We want to think of something else to solve this problem. So let's come back to the brute force. So in brute force, what we discussed, we said that we will be running a BFS or DFS starting from the top left corner for every query, for 5, then 6, then for 3, right? And we have already discussed that the time complexity of this will be k into m into n, right? Okay. Now let us try to observe a few things, or let's try to see a few things. So one thing is very clear, that for every query we will have to start from the top left corner, and in this case top left corner is having value 1. So we'll always have to start from 1, whatever BFS or DFS that we are running for any query. Okay, if this top left corner have a value smaller than qi, let's say we are at ith query and the value for that is qi. So if 1 is strictly smaller than qi, then we have two options. We can either visit 2 or we can visit 3, or we can try to visit both, but let's say if we are running a DFS, then we will have to visit one of these first. Either we will have to visit 2 first or 3 first. So out of these two options, can we say that 2 is having higher probability of having value smaller than qi than 3? Can we say that? So if 2 is having a higher probability of being smaller, then visiting this would make more sense, because if just after 2 we'll go to 2, if we try to visit 2, then we have higher probability that this will also be smaller than qi, right? So let's say we visited 2 after 1. Okay, if 2 is also smaller than qi, then we can now traverse either 4, either 5 or this 3. So these 3 are the new nodes that can be traversed. So out of these 3, can we say that 3 is having the highest probability of being smaller than qi? So we would want to traverse this first. So we would want to traverse 3 first, right? Okay. Now once we visit this 3, then we can say that okay, 5 is already here. So we have one more node which is 4, which will come here, right? Now out of these 3, can we say that 4 is having higher probability of being smaller than qi? So we'll try to consider both these 4s before 5. So we'll try to consider these 4s. So now if you consider these two nodes, then the new unvisited nodes are 7 and 5. So 7 and 5 will come here, right? Now out of these 3, can we say that 5 will have higher probability of being smaller than qi? So we'll try to consider 5 first. Okay. So once we have considered both these 5s, then we will get one more value, which is 4. And out of these two values, we can say that we will want to consider 4 first, and after that we are only remaining with 7, so we will try to consider 7 at the end. Okay, cool. So this would be the preference. This will be the sequence of preference for us for any particular query. So if we just consider this first query where value is 5, so we will start from the top left corner, which is 1, and after that we would want to consider 2, then 3, then 4, then 4. Now we can say that we can't consider any node in this range, and the reason for that is we have built this sequence in such a way that smaller values come first, like all those nodes which are reachable. In those nodes, the nodes having smaller value comes first. That means if we would have any value which is smaller than 5 and would be reachable before this 5, then that value would have been present before this 5, right? So if we reached a value which is greater than or equals to this particular value, that means after this, like starting from this particular element to all the elements which are present to the right, they were either not reachable from all these nodes, or they had a value greater than or equals to this particular value, right? Similarly, if we talk about the second query in which we have value 6, in that case we will start from 1 and we will go all the way till here. Now we got the value which is greater than 7. So we can say we will be able to traverse all these nodes except this particular node. And if we talk about the third query, then we can say that we will start from 1, then we would want to consider this, and once we are able to visit this, then the second preference would be to visit this. Then now we will not be able to visit this or any of the nodes after this, because all these nodes after this are having value either greater than 3 or are not reachable from these two nodes. Okay, cool. So can we use this idea and try to find out our answer for every query? So if we have this particular sequence, then can we find out the answer for our queries very efficiently? So can we say that, let's say for this 5, if we are able to find out the first occurrence of an element which is having value either equal to or greater than 5, then can we say that all the elements starting from this index till the last index will not be visited for this particular query, right? So if we are able to find out the first occurrence of an element having value greater than or equals to the ith query, then our job is done. We can just simply find out this index, and then we can find out that how many elements we can visit. So for this, what we can do, we can traverse this sequence, and then we can find out what is the first occurrence of a particular element having value greater than or equals to the ith query, right? But that will take order of m into n time in worst case, because the size of this sequence will be m into n, because we are considering all the elements of this matrix. Okay. Now can we optimize on this? Can we optimize on this? Right now what we are doing is we are iterating and finding out the first occurrence of an element having value greater than or equals to this particular value. So can we optimize this thing? So here can we say one thing that here can we say that any node after this or any element after this will be visited if and only if the query is having value greater than 1. Can we say this thing? So we can say that any element having value greater than 1 will be able to move forward or visit other nodes present after this particular element. And for this element, what we can say? Can we say that any query having value greater than 2 will be able to move forward or visit nodes after this? For this we can say any query with value 3, for this we can say any value with query 4, and for this also we can say any value with query value 4 will be able to visit the nodes after this. For this 5, for this 5, and now for this element also the value will be 5. Why? Because to reach this element we will first have to traverse these two elements, and if we have to traverse these two elements then we require a value which is greater than 5, right? Similarly, to reach on this cell or any cell after this, we will require at least a value greater than 7. Okay, cool. So now based on this sequence, can we say that it will always be a sorted, or can we say it will always be a increasing sequence? Not exactly increasing, but it will be monotonic, it will be non-decreasing. It will either remain constant or it will keep on increasing, right? So we can say it will be ascending, it will be sorted in ascending order. Now, because this search space, like this sequence is sorted in nature, then can we use binary search to find out the first occurrence of an element having a value greater than or equals to a particular query? We can use it, right? So if we use binary search, then can we say that the time complexity to find out that will be log of m into n, right? It will be log of m into n, okay, for every query if we have already calculated this thing, this sequence, or we can say it will be a prefix max. So if we have already calculated this prefix max, then we can find out our answer for every query in just log of m into n time. Now let's see how much time this sequence will take to build. Okay, so in starting we just consider the first element, which is 1, right? And after that we had two options, 2 or 3, and out of these we picked 2, then we removed it from here. Then after that we have some options, let's say 5 and 4. Now we would want to pick 3 because 3 is the minimum element, right? And after this 3 we will also have this 4. Okay, now we would want to consider 4. That means it will be very good if we have this data in sorted form, right? If we have this data in sorted form, then it will be very easy to find out the minimum element, right? So for this what we can use is we can either use heap, because we are always interested in the minimum element of this, right? So we can either use min heap or we can use set, right? Because set will also have these elements in sorted form, and we can just consider the first element, right? Okay, and every time we would just want to consider the first element, and we would just want to remove this from here, and we would just place here, and we would want to place the adjacent elements of this inside this particular heap or set, whatever we are considering, right? Okay, now every node will be inserted in and deleted from this heap or set at most once, right? Okay, so if it will be inserted and deleted at most once, and if you are using set, then that operation will take log of let's say m into n, because the size of this heap or set can never exceed m into n. And in heap, insertion will take a log of say like same time to insertion, but for deletion it will take order of n time, right? So whatever we use, in worst case every query will take log of m into n, and we will do insertion and deletion at most m into n number of times, so the overall time complexity will be this. Okay, cool. And space complexity will also be same, m into n. All right. Okay, now you guys can try to code it yourself. I think it should not be very difficult after the first approach which we have discussed. And if you face any difficulty while implementation, then you can comment down below and we can try to help you with your implementation, right? And you can, like, while commenting, please make sure that you share your code if you have any doubt in that. All right, so I think that's all for this video, and I'll see you in the next one.